From the review sheet that I distributed, we have a satellite circling a communication satellite, and says assume the radius of the Earth is 3,960 miles. So that means this distance right here is 3,960 because it says assume the radius of the Earth. And the satellite hits at a point that is going to be tangent to the circle. That's why that second picture was drawn for when we're trying to figure out the horizon circle. All right. It says find the formula for alpha in terms of t. Alpha is right here. That's the angle that's halfway. So this is the distance the satellite is above the Earth from its center. And then we consider the fact that it's a right triangle. Right here, this is a right triangle. And sine is equal to, of alpha is equal to opposite over hypotenuse. And as we look at that, we say, okay, the opposite is going to be equal to, let's move this up here. So what I'll have is sine of alpha equaling 390, 60, which is the opposite, divided by the hypotenuse. So in this case, the hypotenuse will be 3,960 plus t. And t was given in the picture as the distance from the satellite to the Earth. So in this case, they're not talking about t in terms of time. They're saying what we're going to do there. And then we need to find what it says in part A is find the formula for alpha in terms of t. So then the next thing we have to do is say alpha of t. Yeah, those background sounds, I have two dogs, and they're playing together, and every once in a while one will bite the other, and he was yelping, so that's okay. You'll get over it. So alpha of t is going to be the inverse sine. Well, let's just go like this. What I need to do is I need to solve for t. So I'm going to take the inverse sine of both sides of sine of alpha. And that is going to be the inverse sine of this whole fraction, leaving me with alpha equals sine of 3,960 over 3,960 plus t. And that would then be my alpha in terms of t. That's my equation for alpha of t. So, it's got to make sure I get this in here. It's inverse sine of what I'm doing there. Part B then asks if t is 30,000 miles, what is alpha? That is, what percentage of the circumference of the Earth is covered by the satellite? Question. That's the second question. And then what would be the minimum number of such satellites required to cover the full circumference of the Earth? So lots of stuff going on here in Part B. But the first thing first, we need to find out what the value of, so alpha sub t is equal to the inverse sine of 3,960 over 3,960 plus t. Putting 30,000 into this equation, you're going to have the numerator of so inverse sine 3,960 over 30,000 plus 3,960. And then that would be alpha of 30,000 is going to equal 6.696 degrees. And when we're looking at the Earth, the next question asks us to find the percentage of, it's probably not a great, so it's this to here. And this was a portion of that triangle. Remember, the triangle went all the way out here. So this was 6.696, which means this angle here, because that's 90, that angle there in the center will give me 83.3. 83.3 degrees, because the second half of the question for part B asked what percentage of the circumference of the Earth is covered by the satellite. So what percentage of the circumference? So they're asking for what percentage of this length. So they've got this length here, and then we've got this length here. So where we're going to go next, it's really twice the angle. So if 83.3 degrees and we're at the center, then this one's also 83.3 degrees for a grand total of 166 point, if we didn't round, 608 degrees is that full middle central angle. And this is the angle of so this is the coverage, how much of the circumference. So what percentage of the circumference? 166.608 divided by 360 degrees. All right, because we're working in degrees here. So that gives me a grand total of 46.28% of the circumference is covered. And if we're thinking, okay, well, then how many satellites would that take? So if one satellite can cover 46%, how many satellites would I need to cover the whole circumference of the Earth? So 360 divided by that number, and that gives you that I'd need 3 satellites to cover the full circumference of the Earth, which would be the entire Earth itself. Part C is just a duplication of Part B. What you end up finding for Part C, if you do the calculations, the inverse sine of 3960 over 3960 plus 1,000. You're going to find that your alpha value there will be 52.976-ish degrees. And then from there, it's 90 minus that to find the central angle. Again, that would be then finding this angle here, and then double that for the full angle. And what we find is that with only 1,000-mile satellite, can't think of the right word, where it's orbit, there we go. It's only going to cover about 20% of the total of the Earth's circumference. Therefore, you'd need 5 satellites to cover the Earth's circumference, because again, 20% times 5 gives you 100%, 20.6% technically. All right, and then Part D. Now for Part D, now we're asked to find how high I would need it to be in order to cover 20%. So 20% of the distance here. I'm going to remember the rest of my triangle is going out. Okay, granted I did not draw that to scale. Try like this, I guess. Here, the key is this is supposed to be a 90-degree angle, so I apologize, it's not looking like it. This is alpha. This is 90 minus alpha, like we've been doing on the others. And I want the full arc to be 20%. So 20% of 360 is 72 degrees, half of which is 36 degrees. And I want the 90 minus alpha to be that 36 degrees. So I really want alpha to be 54 degrees. Oop, that's a big degree mark. 54 degrees. So if alpha is 54 degrees, I'm asked what will this length from here to here be for t? So I can go back to that original equation, and where I had alpha of t is 3960. Sorry about that. Inverse sine of 3960 over 3960 plus t. But here I'm told that I know that my alpha of t is 54 degrees is equal to inverse sine of 3960, 3960 plus t. I need to take the sine of both sides because that's the inverse operation. So if I take the sine of everything, I would then have the sine of 54 degrees being 0.809. This equals then 3960 over 3960 plus t. Algebra, multiply that around. And through algebra, you can see that it, well, I didn't show it all there, but you end up with the total distance t being 934.86 miles, give or take, depending on how you rounded and where you rounded. That's how high above the Earth that it would need to go. And that's the biggest question on this review packet. From here, it'll go pretty quickly as I work through the rest of the solutions. The next question is really kind of looking at different graphs and seeing if you can remember what they look like. And there's ways to work through it real quickly. I typically look at and say which ones, look at their end function, what's going on as x approaches infinity or x approaches negative infinity. So if I have something like this, and this is like for many people the super easy one, that's y equals x, that's a linear equation, so that's here. But you're looking and saying, okay, as x approaches infinity, what does this approach? Also approaches positive infinity. As x approaches negative infinity, so does this. When x is 0, y is 0. But then also remembering that when there's no exponents on the x variable, it's going to be a linear equation. As soon as we add exponents, now we're looking to say, hey, is it even or odd? And odd means it's a like 2, 1, 3, 5, 7, etc. So 1 would be this one, and that's linear. As it approaches infinity, it goes up. As it approaches negative infinity, it goes down. All odd functions are the same way. So cubed would mean as x approaches positive infinity, the equation goes all the way up. As x approaches negative infinity, it goes all the way down. But it's also a curved equation, which makes this the y equals x cubed graph, because as x approaches infinity to the right, the graph is going up. As x approaches infinity to the left, the graph is going down forever, and it's a curved function. Even functions like squared to the fourth, to the sixth, etc., that means both ends of the graph will either be going both up or both down, since this is a positive x squared. That means both ends of the equation, because if I put a negative number in here, square it, it's positive. Put a positive number in here, square it, also positive. So this will always be positive in both sides. So that means for an x squared, since it's positive, again, it's both going up. So these are both positive, but it ends up being like this one here. So x squared, you remember, is a parabola, quadratic equation. All right, so we've checked off this one, and this one. Those are kind of the easy ones. Some people remember that absolute value is V-shaped, so when you're looking at your graph, because absolute value means it turns anything positive that's in there. So as x approaches negative, this goes back up, but it's also a power of 1, which means it's linear. So linear down, linear going up in the positive, going up towards the negative. So this is my absolute value function. And from there, then it gets to be a little bit more trying to figure out which one goes where. Square root is the inverse of squared, which means it would be a parabola laying on its side, which is this one, but only half of the parabola is there because the square root of anything is always positive. If I put in a negative, I can't do anything with it because you cannot take the square root of a negative number. This would be y equals x, or square root of x. That one's now done. We did this one, 1 over x. As x approaches infinity, 1 over infinity is 0, so it's going to be an asymptote. As x approaches negative infinity, 1 over negative infinity also is approaching 0, but in negative infinity, it's going to be 1 over a negative number, so this will be negative. So coming from the negative side, and then positive be coming from the positive side, positive. And if I put in like a really small number, like 0.1, it's going to be really high. So this one here is my 1 over x function. And now I'm just left with cube root. So cube root is the inverse of cubing. And if you look at cubing here, the one that looks like it is this one here. And actually that is true. This is y equals x cubed. The reason, or cube root of x, not cubed, there we go. The reason why that one is not only in one quadrant or in one portion is because you can take the cube root of a negative number and it will be negative. You can take the cube root of a positive number and that'll be positive. And that ends up being all of those equations. This one here is not. What that would be y equals the absolute value of 1 over x, because then it would be the same thing as 1 over x on this side and then also on that side for that question. Moving on. I'm not going to show every one of these problems, but we're asked to find the inverse of x. If you recall what the inverse is, that's a very, if I take this an xy axis, if I have the line y equals x, and if I have an equation, like we did just in that previous one, like this was x squared, its inverse is if I take this equation and reflect these points over the y-axis. So if I were to take this point here, reflect it over the y-axis, it would be there. This point here would go to there. This point here would come down here, but essentially what we end up with is a parabola turned on its side. So the inverse is to find an inverse function. So if I have, for like number 5, f of x equals 11x plus 7, similar to saying y equals 11x plus 7, the process was we switch out the variables for each other and then solve for y. This would be the inverse function, which would be then x over 11 minus 7 over 11. They're all linear equations, so it's pretty straightforward. Write an equation for the graph. So this graph has both ends going up, so I know that the highest power when I'm done will be a even number, and it's going up, so it'll be a positive even number. I have a 0 at -2, and I have a 0 at 3, which means if I had factored this out, I would have x plus 2 and x minus 3 as two possibilities. And when y equals 3, the x equals 0, because that's my y-intercept. So when x equals 0, y is 3. This, however, is a function that's not a high enough power to do this. If I have 3 curves in it, that means my power is at least 4, which is true because it would be an even number. So how would I make this a power of 4? I could possibly put an x squared out in front. Or what I would consider doing is I would look at what's happening here. What does this shape look like? Looks like a parabola. So I'm going to square this portion of it. And then I look over here at 3. What does this look like? Oh, it looks parabolic as well. I'm going to square that as well. And now I'm up to a power of 4. It's going up and then comes through. However, if I put 0 in here, again, thinking of this point, if I put 0 in, I would have 2 squared, and then I would have times, and I'd have 0 minus 3, with the 0 minus 3 right there. And that would be -3 squared, so that'd be 4 times 9, which is 36. But I need it to be just 3. So how do I make it just 3? Well, if I have -30, let's see, 36, -33 at the end, then it would subtract to 3. So this could be a possible function related to that. And I could, if you wanted to check, you could throw it in Desmos and see if you were close to it. But conceptually, you're getting at the idea of, at my 0, what is it looking like? It's looking parabolic, which is a squared function. At 3, what's it looking like? Looking like a parabola squared. What's it looking at? Like up here, well, it's going to have to eventually come back down, so we're not worried about that. We're mostly looking at what the function is happening at when there are zeros going on. For the next one, it's a polynomial. We know that one of the zeros is at 1, which means when divided into this polynomial, my dividend at the end will have no remainder in it. I can do one of 2 ways. I can actually do it long division, x cubed minus 6x squared plus 11x minus 6. And if 1 is a root, then x minus 1 is the actual factor of that. And then the process is I go x into x squared, that's x cubed, or sorry, I should say x into x cubed is x squared, and I keep it over the vertically aligned for the x squared, and then I multiply x squared times x is x cubed. Again, that was x squared times x is x cubed, then I go x squared times negative 1 is negative x squared. Subtract x cubed minus x cubed is 0. 6x squared, sorry, negative 6x squared minus x squared, but it's minus a negative x squared. So then that would give me negative 5x squared. Bring the next one down, 11x, and that's a positive. I look and say x into negative 5x squared needs to be a negative 5x. So when I multiply negative 5x times x, I get negative 5x squared. Negative 5x times negative 1 is positive 5x. Subtracting negative 5x minus a negative, that's plus a positive, so this is 0. 11x minus 5x is 6x. Bring it down, negative 6. And then again, last one, I'm thinking 6x into negative, or x into 6x, I need it to be plus 6. I would have 6 times x, 6x. 6 times negative 1, negative 6. Subtracting again. 6 minus 6, 0. Negative 6 minus a negative 6, which is plus a positive, also 0, as it should be. So at this point, so far, it's factored into x minus 1, x cubed minus 6x squared plus 11x. Oop, that's the original equation. It's the dividend up top, x squared minus 5x plus 6. If I want to use synthetic division, what I start with is I start with the coefficients of my original equation. So that would be, let's see, coefficient of the x cubed is 1. Coefficient of the x squared is negative 6. Coefficient of the x is 11. Coefficient of the constant is negative 6. If you're ever missing that, say, for example, this x, there wasn't an x squared, this would have to be 0 over here, but it's not. All right, I am going to be then dividing into that. My 0 is 1, so I put 1 there. And then the process is I bring down the first term. The 1 comes down. And then I go 1 times, sorry, this one times 1, and I put it here. 1. And then what I do when I do synthetic division, though, is I add. So then this would be negative 5. And then I go 1 times negative 5 is negative 5. Add. 1 times 6 is 6. Add. So I'm left with x squared minus 5x plus 6, which is the same as what I had on the other one, x minus 1. Last step is to finish that out. Either you can look at roots or you can say, oh, I can factor this, two numbers that multiply to 6 and add to negative 5, add to 6, sorry, multiply to 6, add to negative 5. This is positive, which means both are either positive or negative. Since his middle number is negative, I know that they're both minus 3 and 2. And then I'd be fully factored in that problem. When looking at polynomials, complex polynomials, so polynomial over polynomial, we're going to be asked to find all these things. Procedurally, one of the things I like to do first is if I can, find out if I can actually factor this equation into something. So in that numerator, it would be 2x and x, and then I'm looking for two numbers that multiply to negative 15, add to positive 7, but when multiplied by 2, which means one's positive and one's negative. So I'm going to guess that this is going to be a 5, because that'll give me positive 10. This will be negative 3, so when I multiply FOIL, positive 10 inside negative 3, that adds to positive 7. In the denominator, I'm going to have 3x in one of them, x in the other one. Here again, adding to, or multiplying to positive 15, adding to negative, one's positive, one's negative. And if I have, let's see, 15 and 1, that's not going to help me much. 5 and 3, that's not going to help me much. Well, it's possible that I can't factor that. Remembering though, sorry, multiplying to a positive, so they're both negative. That's better. So 3 and 5, so if this is 3, that gives me outside of 9. And then if this is negative 5, inside is 5x, negative 5x, so negative 9, negative 5, that's negative 14. What that helps me for is that helps me in identifying my vertical asymptotes. What x's can I not have in this whole equation? And I'm looking at and thinking about a graph, of course. I can never divide by 0, which means what makes this 0? It's a positive 3. So at 3, 1, 2, 3, I have a asymptote going on. And then here, what makes this 0? Well, if I set that equal to 0, 3x minus 5 equals 0, so x equals 5/3. At 5/3, which is just before 3, well, that's really close. So at 5/3, and then, and then also at 3, I have vertical asymptotes. Finding my intercepts, vertical asymptotes, check. Horizontal asymptotes are, is there anything I cannot get as an answer over here? Can I never have negatives or something like that? Well, I don't have absolute value. I don't have square roots. Everything isn't always squared, right? Because I will have a negative here. Like if everything were a squared something or another, like if that was a fourth and that was a squared, that means I'm almost always going to have positive numbers. But what I want to look for then is I'm probably not going to have a horizontal asymptote. But let's look at my intercepts. My x-intercepts are what makes this 0. So when x is a certain number, y will be 0. So that will be an x-intercept. So if I put in negative 5, 1, 2, 3, 4, 5, negative 5. When I do that, this is 0. 0 times anything is 0. 0 divided by anything is still 0. And then what in here? And I have, let's see, so what makes this 0? So set this equal to 0. I get 3 halves. 3 halves is 1.5, so that's right here. And next up, y-intercepts. Y-intercepts happen when x equals 0. So if I put 0 into my equation for x, I will have up here 0 minus 3, which is negative 3. The next one I'll have 0 plus 5, well that's 5. 0 minus 5 is negative 5. 0 minus 3 is negative 3. So I will have negative 15 over positive 15. So my intercept is at negative 1. Right there. And then I look and say, all right, how might this equation go? Well, and so that's x-intercepts. I got y-intercepts and tendencies. As I put in larger and larger values for x, I'm going to have x squared over x squared. So these are the most powerful. That's why when we talk about the highest power, it's a second degree polynomial. These will determine what's going to happen with a function. As these get really large, so really what I'm saying is, as x approaches infinity, what's happening? these numbers get so large that these become irrelevant. When that happens, these become so large, and the only thing different amongst them is 2 and the 3 because the x squared. So again, when you put in like a number like 1,000,000 for x, although this would be 7 million, that's 14 million, this is 1,000,000 squared. So these become really decimal place insignificant values. But then the 1,000,000 squared over 1,000,000 squared would reduce to 1. I'm left with 2/3. When these are the same power, my end tendency is as x approaches positive infinity, my graph will approach 2/3. Approaches 2/3. So way out here, if 1 is right here, it's approaching 2/3 as my function. And since it doesn't cross the x-axis, it probably started up here and came down here and is approaching 2/3. All right. As x approaches negative infinity, negative times negatives, that'll be positive, and again, negative 1,000,000, these become inconsequential. And actually, then as x approaches negative infinity, my f of x will also be approaching 2/3. And that kind of makes sense because I've got this graph, it crosses the x-axis, it goes here, and then it's going to approach 2/3 somewhere out there. And then the only last thing to try to figure out is what's going on in between here. It's either going to be up and down or down and up, but you'd have to pick a number in there to know for sure what's going on. So somewhere between 5/3, so, because again, 6/3, well, that's actually 2. I have my graph drawn a little bit wrong. So 5/3 would be just before the 2. So that should be not here. Should be closer to the 2. So if you put 2 into that function, you'll find out if it's positive or negative. If it's positive, then it's going to be something like this. If it's negative, it's going to be something like this. That's how it's going to work for all of those same problems in that section as well. Compounding interest formula, not necessarily an equation I'm going to expect you to memorize, so if you need it, I'll probably be giving this to you in some way. 4,000 invested at 7% over 9 years. So P is the original principal. We start with 4,000. R is the rate, N is how many times a year, and then N times T, T is number of years. So annual, my N is 1, my T is 9, so I plug that in. So A of 9 years, 1 plus 0.07 over 1, which is 1.07. 1 times T, 1 times 9 is 9, 73.53. So after 9 years, a $4,000 investment will yield 73.53. If I do it quarterly, now my N is 4 because it's every 4 years, or every quarter of a year. T is still 9. What changes in the equation? 0.07 is divided by 4 because I'm splitting it up and doing it 4 times per year. So 1 plus this number is 1.0175. And it's raised to the 4 times 9, or raised to the 36th power. This is what I'm yielding. So you can see quarterly, slightly better yield than annually. You can do monthly, follow the same process. It will be slightly larger again. And then continuously use a different function because as n goes up towards infinity, this whole thing approaches E. E is that transcendental number 2.7 and change. So if I do that, I go 4,000 times E to the, now, so the rate is now just the 0.07 times 9. If you do it in your calculators, E to that power, multiply first, then take the power. So is 1.877 times 4,000 is 7510. You can see that going continuously is obviously the best approach. Scientist has this component, and it's radioactive decay. He begins with 100 milligrams. So at time 0, the amount at time 0 is 100. So if I do 100 equals A times, oh, and the A is my original amount, 100 times sorry, in this case, A is not the amount. A is a constant number. So it's A times B to the T, and my T is 0. B to the 0 is 1. well, actually I end up finding out then that A is actually 100. Second part of the problem then says, after 4 hours, it is decayed to 80 milligrams. So at 4 hours, I am at 80 milligrams. So at 80, it's equal to 100 times B to the 4th power. So solving that, reversing that out, so that's 0.8 equals B to the 4th. Take the 4th root of each side. All right, now if you're struggling with that on a calculator, so again, the 4th root of something is the same as saying B to the 1/4 power, or B to the 0.25 power, but either way, so B is going to then equal 9.9457. That's my B, so my full function is A of t equals 100 times 0.9457 to the t power. Last part of the question, how long will the process begin? How long after the process begins will we get to 15? So when does this 15? So that will equal 100 times that whole thing. Solving, we get then divide by 100. 0.15 equals 0.9457 to the t. Inverse of exponent functions is logarithms. A couple ways you can go. If I take the log of both sides, take the log of this. The properties of logarithms means now that that can come down in front, so it's going to be t times log of 0.9457 equals the log of 0.15. Those are just numbers. I then divide both sides. T is equal to, go up here, log of 0.15, which you can do in your calculator, divided by log of 0.9457. If I did this correctly, T will be